So we will continue today talking about convolution of distributions, although we haven't actually started really talking about that because we have lots of preparation to do. Okay. So our first bit of preparation last time was that we introduced a couple new classes of distributions. And so as I said last time, distributions as we define them are, D prime constructed from the specific class of test functions D, but there's other kinds of test functions you can use. Test functions are always assumed to be infinitely differentiable for the purpose of talking about distribution theory. And so, but there's other kinds of properties that you might want to add to your test signals that are different from those for D. So, for D, they have compact support, but there's other kinds of criterion you might want to put on your spaces of test signals. And then you talk about the topological dual of those, once you define convergence. And so the procedure is similar for all of these classes of distributions. You just have to give a notion of what your test signals are and what notion of convergence in that class of test signals is, and then you have continuous linear functions being the associated classes of distributions. And so by that process, I'm making that sound like that's easy, but to make real sense of that requires making sure that all those steps are coherent. But in any case, last time we looked at two classes of test signals. Okay, so B0 were the infinitely differentiable functions on R, for which they and all of their derivatives go to 0 at infinity. Okay, and then we had E is just a class of all infinitely differentiable signals without any restrictions on them. And so we defined convergence in these spaces last time, and then using that notion of convergence, we talked about continuity and then the continuous linear functions on this one we denoted like so. And then the continuous linear functions on this one, we denoted like so. So there's a little bit of an asymmetry that happens in this case, right? So, in the two cases we've seen so far, D and E, the duals are E prime and D prime, but it's a little different here. And that's, mirrors something that happens for spaces of regular functions, not just distributions, where L1 is the dual of C00. Okay. Okay, so now we want to do another construction, and so we're not sure where these are going yet, and that's okay. We'll get there. And I want to do something else where it will also not be clear where this is going, but it all sort of comes together in the end. So let's talk about tensor products of distributions. Okay, so this is a very technical thing if you want to get into proving all of the statements that I'm going to make. Okay, so we're not going to be doing that, and we're not really going to be providing also any kind of a context for what we're doing, because the things I'm going to be talking about sort of fit into some larger picture of functional analysis, where the constructions that I'm going to be doing are specific examples of more general kinds of constructions you can talk about. So we're not going to be talking about any of that. We're going to kind of take the shortest distance to where we want to get to. And as a result, the discussion seems a little concocted, and there's really not too much you can do about that. And the first thing that you have to do to talk about tensor products of distributions is you first have to admit that you need to talk about classes of functions whose domain is not just R, but something more general. Okay, so we can talk about this space, and so I'm just going to do that. I'm just going to talk about it because once we've defined D of R, in the case where n is equal to 1, reasonably carefully, as we've done, the ensuing discussion for the case where the domain is Rn is not complicated. It has the same definition. So D of Rn, F, are the F-valued functions on Rn that are infinitely differentiable and have compact support. Okay, so exactly the same definition. The notion of convergence in D of Rn is exactly the same. And that is that a sequence in here converges if all of the functions in the sequence have their support contained in a common compact set, and if all the functions and all their derivatives converge uniformly on that compact set. Okay, so the definitions are all the same. And there's virtually nothing you have to change there. You know, when you're doing proofs for these things, there's a bit more notation that shows up because you have to talk about derivatives, multivariable derivatives, but it's really literally just notation. Okay, so there's no difficulty in talking about this space. There's no difficulty talking about convergence in this space, and therefore there's no difficulty talking about the space of continuous linear functions on it. Okay, and so you can talk about distributions not just on R but on Rn, and in fact you can talk about distributions with more general domains than that. Okay, and this applies similarly to all the kinds of spaces of distributions that you talk about. And we're going to have other spaces of distributions that we're going to talk about later. And these kinds of extensions from a single variable to multivariables, those also apply in those cases. Okay. All right, so that's the first thing you have to do. And then when you talk about tensor products, what we want to do is we want to take two distributions, let's say theta and rho, and we want to define what we will call their tensor product. Okay, and this is going to be a function of two variables, or a distribution on the space of two variables. Okay, now each of theta and rho take a test function, which is a function of a single variable. And so the first thing you want to do to try to understand this construction is to see what's the relationship between test functions of two variables and test functions of single variables. And so it's not clear what that statement means, but what that statement means is this. Okay. So if phi, sorry, before I state the theorem, I should introduce some notation. Okay. So if phi and psi are test functions of a single variable, okay, then we can define so we're going to define a test function of two variables in kind of an obvious way. So it's going to be a function of two variables, say s and t, and we're just going to take the function of s and t, which is phi of s times psi of t. Okay, so we're going to denote by phi tensor. So we have this thing that we introduced in a super specific setting if we're talking about differential equations, the tensor, this tensor notation. Okay, so this is another variant of, so there's a larger framework in which those two things are kind of the same. Okay, but we're going to write phi tensor psi of, so this is going to be a distribution, sorry, a test signal in two variables. And it has the obvious definition that phi tensor psi of s and t is phi of s psi of t. Okay, so this is clearly infinitely differentiable, and it also pretty clearly has compact support. Okay, then theorem. If we take a test signal phi in d of R2, okay, then there exists a sequence of test signals phi j, and these are still test signals in two variables, but they are of a specific form. Namely, they're going to be linear combinations of these. Okay, so these are okay. So these phi j's, they're going to be in span. Oops, span R of notation to use here. So in the absence of something better, I'm going to write these as mu tensor nu, where mu and nu are test signals in one dimension. Okay, and so let me just try to clarify what I'm saying here. I'm saying take this, so this is going to be some subspace, okay, and the phi j sequence is going to be in that subspace, and so this is just going to be the subspace spanned by all distributions in two variables obtained in this way. Okay, so this is going to be a subspace of d prime, prime d of R2F. Okay. Okay. Okay, so there exists a sequence phi j in here. Okay, so each phi j is a finite linear combination of things that look like that. Okay, and a sequence of test signals there converging to phi in the topology of the space of test signals on two variables. Okay. All right. So it doesn't mean, of course, that that every phi is in here. Okay, but it means that every phi is a limit of things in here. Okay, so this is rather non-obvious, and in fact, the proof of this theorem, there's multiple ways to prove it. One way to prove it is actually to use convolution. And so you construct these things phi j as convolutions. Okay. Or I shouldn't say as convolutions, using convolution. All right, but the proof is a bit technical. Okay, and you know, if you want to dig deeply into this, and it's interesting to do so, what this says is that this vector space with its topology is isomorphic to this vector space. Okay, and this tensor product here is what's known as the projective tensor product. So you put a pi there, and it needs to be completed. Okay, so there, the main point of that little comment is there's a general world in which this theorem is a special case. Okay, but we're just going to take this big hammer that we already have from somewhere else. Okay. Okay, good. So now we use this construction to define the tensor product of two distributions. Okay. All right. So now let theta and rho be distributions in the single variable. Okay. All right, so what I want to do, as I said up here, is I want to define their tensor product as a distribution in two variables. Okay, so I'm going to take a test function phi in two variables. All right, and first. Okay, so sorry, notation. Denote phi s of t to be phi s t. Okay. And so the point is that when I fix s, okay, phi s now becomes a test signal in the single variable t. Okay, so one can, and again, not easy, not super hard. I don't want to make it sound like these are incredibly deep results, but you know, they're definitely not obvious. Okay, so one can show that if you go all right, so in this setting, we fix an s, and then we think of the resulting test signal as a function of t. Okay, and then what we're going to do is we're going to take phi s, and we're going to act on it with one of these two. It doesn't matter. We'll make it arbitrary choice, rho. And so rho is going to act on the test signal phi super s, okay, for s fixed, and then we're going to think about how that thing varies as a function of s. Okay, so we're going to take the function of s, which is defined by rho of phi s. All right, so that function of s now is actually in D. Okay. All right, so you have to prove that. Okay, and you might want to try to get a handle on this. You might want to think about trying to look first at the case where rho is maybe theta f, right? So rho is the distribution corresponding to a locally integrable function, and sort of see how that might arise in that case. Okay, but it's true in general. All right. Okay, so we're going to call this function. And it's, remember now, it's a test signal. Okay, we're going to call this phi rho comma phi. All right. So then we can define the tensor product of distributions as follows. Of theta and rho. Okay, is theta tensor rho. So this is going to be what I asked for, a distribution in two variables. Okay, and so it's going to be theta rho taking a test function phi in two variables, just like I had here. Okay, and it's going to be theta applied to this test signal. Okay, so the idea is first I hit rho with, I hit phi with rho, okay, fixing one of its arguments. Okay, then I take the resulting function of that fixed argument, think of that argument as variable, and hit it with phi with theta. Okay, so that's the idea. Okay, and the construction at least makes sense because this thing is in D. All right, so properties of the tensor product. Of distributions. Okay. So while it's true this construction makes sense in the sense that it defines for you a number, right? So the definition gives you a scalar. To show that this is a distribution, you still have to prove continuity. All right, so there's still that to prove, and that's true. Okay, so first, the definition is well posed. So it is a distribution. Okay, that means must show continuity. And that's not that hard. Okay. All right. Convolution. Tensor product. So how does this construction play into that? Well, if you take test signals phi and psi, and you take their tensor product like this, you get something in distributions in two variables, and then you can ask what's the tensor product applied to such a test signal. Okay, and so that's what this property is. So if you go theta tensor rho acting on phi tensor psi, okay, so this is the very specific test signal in two variables defined by phi of s psi of t. Okay, that is kind of what you hope it is, which is theta of phi rho of psi. All right, so that's pretty obvious if you just look at the how this thing is constructed. Okay, but that's not the most important part of this. And theta tensor rho is the unique distribution with this property. Okay, so in other words, if you have a distribution which has the property that when you apply it to a tensor product of test signals like this, you get that. Okay, that distribution must be this one. Okay, and the uniqueness here comes from the theorem. Okay, because the theorem tells you that every test signal here can be approximated by linear combinations of tensor products like this. Okay, so that's the uniqueness property. Okay, so in this construction here, I made a choice by fixing S and thinking of this thing as a function of t, but you could have done the other thing, and then you could have then contracted first with theta, contracted first with theta instead of rho, but the point is it doesn't matter. Okay. And you can see why it doesn't matter, sort of from there already. Okay, and so the point is that theta tensor rho is rho tensor theta. Okay, so this tensor product is commutative. It's also associative. Okay, so we're not talking about convolution here yet, because this associativity property is not true for the convolution product, but it is true for the tensor product. Okay. All right, so so that's the tensor product of distributions. Okay. Now, how do you use that to talk about convolution? All right, so finally, we're going to get to where we wanted to get to. Okay, so first, so that we can get some appreciation for what's going on here, let's first take another look at convolution of just ordinary signals. Okay, so let's let f and g be locally integrable. And let's look at a test function phi of a single variable here. Okay, so let's look at the convolution as a function. Okay, so we're going to suppose that fg is convolvable and just sort of do a calculation here. Okay, and the calculation that we're going to do is we're going to take this thing. Okay, and so we know that if fg is convolvable, that I said, and it's not easy to prove, but I said that the convolution is in L1 loc. All right, so therefore this thing makes sense, and so I can feed it a test signal as an argument. All right, so let's just do some calculations. Okay, so this is going to be the integral over R f star g of t phi of t. All right, and provided that the pair fg is convolvable, then this integral will always make sense. Okay, but the convolution itself is given to us by some integral. Okay. All right. So then you can just make a change of variable. Okay, so you can call this tau, and do the resulting change of variable. And what you get is this is the interval over R. And you can also, when you do that, you can change the order of integration as well by Fubini's theorem. And so Fubini's theorem is a theorem about changing the order of integration. And so you have to verify that this argument here, this integrand, as a function of the two variables s and t, satisfies the conditions of Fubini's theorem. And we're assuming that f and g is convolvable, and that's enough to do that. Okay, but the point is, after you do all of that, what you get is you get f of t, g of s, phi of t plus s, ds dt. All right. Okay, and now, why did I do that? Well, I did that because this thing here is really representative of theta f tensor theta g. Okay. If you take a function f of a single variable and g of a single variable, take the distributions corresponding to those, then the tensor product of that distribution as a function of two variables is exactly going to be the distribution corresponding to that. Okay. Okay, so the point is, this is some distribution in two variables. Now, what's this thing? This is phi is a test signal, okay, but okay, so the problem here, and this is the problem with taking convolution of distributions, is that this function, as a function of two variables, does not have compact support generally. Okay, and so in other words, you can't just take this function of two variables and feed it to this distribution in two variables and expect to get an answer, because this thing is actually not a test signal in two variables. It's a test signal in a single variable, which you use to build a test signal in two variables by this device. Okay, and the issue is sort of something like this. If you think of how the function phi is defined as a function of two variables. Okay, so let's say this is s and this is t. Okay, and let's say the support. So we know that the support of phi is compact. Let's suppose that it's some compact interval, so that I can draw it. Okay, so there's a corresponding compact interval in the t variable. Okay, and then support of the function. Oh, sorry, I made a mistake here. I apologize. That's s plus t. Okay, the support of the function of two variables, phi of s plus t, is going to look like this. Okay, so it's not compact. Okay, so if you're going to use a formula like this to motivate your construction of the convolution of two distributions by how they act on a test signal, you're going to need some additional stuff to ensure that the construction makes sense. Okay, so and there's various ways of doing that, and we're going to look at one way of doing that, but you kind of need some, compatibility conditions on on the two distributions. In this case, the distributions are theta f and theta g, but generally they could be theta and rho. But you need some kind of compatibility conditions to ensure that the convolution exists, meaning that when you give it an argument of something like this, this function of two variables, that somehow makes sense. Okay, because it doesn't make sense just on its face. All right. Now, a common way of doing that is to assume that one of these two distributions itself has compact support. And then if that's true, then that sort of obviates the problem here, because let's say it's this distribution which has compact support. So its support is going to interact with the support of phi, and so you only have to worry about a compact subset. All right, but that's very unsatisfactory. You don't want to restrict yourself, for example, to a theory of distributions which only generalizes the convolution of functions in the case where one of them has compact support. That's really unsatisfactory. Okay, so we want to have a theory of distributions which generalizes of convolution of distributions, which generalizes the theory of convolution of functions that we've already defined. Okay, and so it takes a little bit more care, and that's why we introduced the notion of integrable distributions, because that provides us with a device for doing that. Okay. All right. Okay, so here's how you do that. Okay. Okay, so now I'm going to make use of this thing we talked about last time, which is the space of integrable distributions. And here we're going to use integrable distributions in two variables. Okay. All right, so first, distributions theta and rho are convolvable if for every phi, and so phi now is going to be a test signal in one variable. Okay. The distribution okay. So now the distribution is going to be a distribution in two variables, and the distribution is going to be defined like so. So I'm going to take a test signal, psi, in two variables. Okay. And I'm going to do the following thing. So I'm going to take theta tensor rho. So I know that that's a distribution in two variables. So it's looking for a test function, which is a function of two variables. And the test function I'm going to give it is going to be this one. It's going to be psi. And then I'm going to take this function tau star phi. Okay. So first, let me say the words, finish the words here. The distribution like this is in D prime L1 R2 F okay, where tau star phi of S and T is phi of S plus T. Okay, and so tau star phi is phi composed with tau, where tau of S in T is S plus T. Okay, so I have this simple function tau as a function of two variables, which just combines the arguments like so, and then phi is just that. Okay. All right. So the point is now is that this function by itself, okay, as I've talked about up here, is not a test signal in two variables. However, if I multiply it by a test signal in two variables, psi, because this has compact support, it's going to take the possibly non-compact support of phi, and it's going to intersect it with the compact support of psi, and the resulting thing will have compact support. Okay. All right. Okay. So that's what it means for a pair of distributions to be convolvable. Okay, so and what this amounts to is this amounts to saying that in this case here, okay, this is what I'm gonna do is I'm gonna stick in psi of S and T in here, and I'm gonna require that the resulting thing be an integrable distribution. And so one of the things you can prove is that the condition for convolvability of distributions exactly generalizes the condition for convolvability of functions. Okay, but I'll say that carefully in a second. Okay, so that's what convolvable means. Then what's the convolution? Okay, so if theta and rho is if the pair is convolvable, their convolution is obtained in the following way. Okay, so first of all, it's theta convolution rho in D of R F. Okay, so it's of course a distribution in a single variable. Defined by, okay, so theta convolution rho applied to a test function phi of a single variable is equal to the limit as j goes to infinity, theta tensor rho applied to psi j tau star phi. Okay, so I have the same kind of construction as happens up here in the definition of convolvability. Okay, but now I'm going to take a sequence of test functions psi j in in two variables. Okay, and this sequence should have a very particular property, and it's this property that we talked about last time of being a special approximate unit. Okay, is defined by this for a special approximate unit psi j, and I'll remind you just in words what that means. So that means this is a sequence in here. Okay, so these are compactly supported infinitely differentiable functions, and they have the property that on any compact subset of R2, because they're functions of two variables, there's a sufficiently large value of the index so that all of the test signals beyond that have the value exactly 1 on that compact set. Okay. So you can think, for example, of taking a sequence of balls in R2 that grows in radius, so maybe radius 1, 2, 3, 4, 5, and so on. And this sequence psi j might have the property that it's identically equal to 1 on the ball of radius 1. And it tapers off to 0 outside that ball, and then psi 2 would be 2 on the ball of radius 2, and it tapers to 0 outside, and so on. So I drew that kind of a picture in one variable last time. So this is the multivariable generalization of that. Okay, so that is the convolution of distributions. Good. So for me, the most important thing here of a satisfactory theory of convolution of distributions is the following fact. Okay, that a pair FG in L1 loc F is convolvable if and only if their corresponding distributions are convolvable. Okay, and moreover, the convolution of distributions is the distribution of the convolutions. Okay, so the convolution of the distributions is the distribution of the convolutions. Okay. All right. So this isn't the standard theory of convolution of distributions, such as you'll see in most books that talk about convolution of distributions. So you have to dig into the research literature to find this construction, but it's certainly a construction that is as understandable as anything else in distribution theory. And it's certainly, in my view, no harder than talking about convolution as it's normally talked about. So when you normally talk about convolution, you still have to talk about the tensor product. So you don't avoid that bit of technicality. The only thing that you need to do here on top of the normal discussion is you need to talk about this space of integrable distributions, okay? Because that's where you get the notion of convolvability. Okay, so that's good. So let's just look at a very simple example, just to see how the mechanics of this works. So take an arbitrary distribution. Okay, and we're going to show that any distribution can be convolved with the Dirac distribution, and the convolution of any distribution with the Dirac distribution is the distribution itself. So in other words, the Dirac distribution acts as a unit with respect to the convolution product. Okay. So we claim that theta delta is convolvable and that theta convolved with delta is theta. Okay. All right. So first, let's let phi be and psi. So phi is a test signal in one variable, and psi is a test signal in two variables. Okay, like I have up here. All right. Okay, so then, all right. So first, let me fix a value of s. Okay. Okay, so let's go delta acting on psi tau star phi. Okay, and so let me do it like this. Okay, because remember that the so what I'm doing here is I'm looking at the definition of tensor product. Sorry, where is that? Right here. Okay. Right. Okay, so I'm using this construction here, and I'm taking theta to be theta, and I'm taking rho to be delta. Okay, so I'm defining the tensor product. I'm computing the tensor product of the two distributions. Okay. All right. Okay, so what's this? This is by definition of the Dirac. So S is fixed. So the Dirac says take this and evaluate it at this test signal is a function of now with S fixed is a function of just the variable t. And so I take this thing and I evaluate it at S and then at t equals 0. Okay, so in other words, this is psi of S0, okay, phi of S plus t, but I'm taking t to be evaluated at 0. So let me just write that in like so. Okay. All right. So now, so first of all, so this always makes sense. And then what I want to do is I want to now evaluate theta tensor delta on, to calculate theta tensor delta, I'm going to take theta and I'm going to act on this function of S. Okay. Okay. So this acting on psi tau star phi is going to be equal to, all right, so so the definition is that it's theta of phi rho comma psi phi, all right, or sorry, not psi phi, but psi tau star phi. Okay, that's the definition. All right. Now, what I'm going to do is I'm going to choose psi large enough that, sorry, I'm going to choose psi in such a way that, okay, so choose the test signal psi so that psi of S0 is equal to 1, okay, for S in the support of phi. Okay, so why am I doing that? Well, I'm doing that because look at this expression here, okay? So if you choose psi test signal of two variables, S and T, with this property, then this thing is just going to be phi of S. Okay. And I know that I can always do that. And now this, you can see the shadows here of this special approximate unit showing up, right? The supported phi is a compact set. And so you can choose size so that on a large enough compact set, which, contains, the supported phi across 0, that psi will be equal to 1 on that set, okay? All right, so if you do that, okay, and then what you get is you get that phi tensor delta of psi tau star phi is equal to, so it's theta acting on this test function, okay, but I've chosen psi so that this test function is just phi, okay. Right, and so the point is that this is just theta of phi. Okay. And so what does this show us? Well, this shows us exactly what we wanted. So therefore, if psi j is a special approximate unit, then for large enough j, okay, and so here I'm making use of this fact, right? So for j large enough, psi j will have that property, okay? And so then you're going to have that theta tensor delta of psi j tau star phi is equal to theta of phi, okay, for every large enough j, and so therefore certainly the limit as j goes to infinity will be that. Okay, and so this, all right, this after, now remember, this after all is just a definition of the convolution of theta with delta, right? That's our definition of convolution. Okay, all right, so thus theta convolution delta is equal to theta. Okay. All right, so I kind of I left out a step here, which is to show that this is convolvable. And the reason that it's convolvable here is just exactly because delta has compact support. Okay, and so if you look at the definition of convolvability here, okay, we have rho here as delta, which has compact support. Okay, and so when you take the tensor product as a function of now two variables, okay, one of them is going to have compact supports. In this case, it'll be rho, which has support just equal to the set 0. And so, as I kind of argued previously, if you have a distribution with compact support, so in this case, it's compact support is a function of t, and so the support is going to be contained in some compact set here. And so when you take the intersection of these, you're going to get a compact set. So the thing that happens here is that because rho, which is delta in our case, has compact support, even if you don't multiply by psi, rho kind of acting on this thing, which remember is how we do the tensor product, right? We take rho and we fix a variable and we act on that test function. But this thing doesn't have compact support, but because rho has compact support, when we take this function of two variables and we hit it with rho, we're still going to get something in D of a single variable back again, even without having to sort of chop it off to zero by this thing here. And so that's why you get convolvability in this case. But it's because although this does not have compact support, this does. And so when you construct the tensor product, you fix one of the variables here, and then compact supportedness of this thing forces the resulting function to be to also have compact support. Okay, so we'll see this when we talk about distributions with compact support later. Okay, so the point is of that messy discussion is that this pair is always convolvable, okay, for any theta, and that the convolution acts as an identity. Okay, now this does not mean that this is a nice a ring with a unit, right? So it has a unit, but it's still not the case, of course, that every pair of distributions is convolvable. It just means this pair of distributions is convolvable. All right. Okay. All right, so let's now talk a little bit about some properties of convolution, apart from the one that I already gave here, which as I said before, to me is the most important one, which is that the convolution of distributions as defined here generalizes the convolution of functions. Okay. All right, so convolution of distributions is commutative. Okay, so this means that if theta rho is convolvable, then rho theta is convolvable, and the convolution of theta, theta star rho is equal to rho star theta. So it's linear, or maybe more properly, bilinear. Okay, so linear in each argument theta and rho. Okay, but as with functions, it's not associative in general. So you can come up with distributions, three distributions, so that so up here we had the tensor product was associative, so, but this property does not hold for convolution. Okay. All right, so this is rather like what happens with convolution of signals. Okay. So let's look at some special cases of convolution, just like we did when we talked about signals. We looked at convolution. We looked at convolution for functions with their supports satisfying certain properties. So we particularly were interested in the case where the supports were bounded on the left, and we'll look at the same thing here. So convolution for distributions with restrictions on their support. Okay, so the statement here is, so what happens here is rather similar to what happens with signals, okay? So if theta and rho are in D prime plus of R F. Okay, so that means their support, the support of the distributions is bounded on the left. Then it's always the case that the signals can be convolved. Okay, and the convolution is also has support bounded on the left. Okay, so you can't give the same kind of explicit formulas in terms of integrals that we gave in the case of talking about convolution of signals, but you get similar results, similar flavor results. Okay. Okay. So convolution here. So the convolution here is associative in this case. Okay, which is not true in general. Okay, and so what I mean by that is, of course, okay. All right. Okay, so then now, and so we're doing something kind of we're trying to mirror what we did a little bit in the case of signals, so the next thing that you would talk about, and we'll maybe talk about it next time, is we'll talk about convolvable, special kinds of convolvable pairs. And so remember that for signals, we had L1 loc, well, sorry, we had L1, L1. So if FG were in L1, then the convolution is in L1. Then we had LP, LQ, LR, the Young's inequality stuff. Okay, so we're not going to get results exactly like that for distributions. We're going to get results that look a little bit different. So we'll talk about that next time. And we'll also next time talk about periodicity of distributions and convolution of periodic distributions. All right, so that's next time.